be recording today's program. Okay, so Mark, please take it away.
Awesome. Thanks, Christine. So we'll go kind of quick today through the slides. What was that? And then if you could save your questions to the end, if you got something that pops up at one of the slides, feel free to throw a question into the chat, and we'll make sure to get to that when we can accordingly. So today's overview, right? We'll just, we'll discuss the high-powered rocketry vehicle structure. We'll talk a little bit about structural design process, and then we'll do a materials overview, which is kind of important for this year's challenge. It's mostly a materials-driven challenge as well as structure. And then we'll talk about structural analysis process, which is near and dear to my heart because that's what I do in my day-to-day job at Blue Origin. And then we'll talk about structural test process, components. We'll talk about manufacturing and integration process, which is very important. A lot of people tend to overlook the manufacturing and the integration side of it, and that's where you run into problems in flight or post-flight. And then we'll talk about structural test process for the vehicle. And then we don't have on the overview, but we have some housekeeping admin slides at the end to discuss and share with you. So vehicle structure, right? There's an image of the actual rocket and then a high-powered rocket on the left, actual rocket on the right, very similar. And then so you can see the nose cone at the top and working down. I'm not going to read through all of those. But in my mind, as a structural analyst, I kind of narrow, I always tend to group things into buckets. So you see the nose cone is a conical shape, airframes are cylindrical, fins are plates, bulkheads are plates. So you're basically just looking at tubes and plates from a structure standpoint. And then, once you figure out how to analyze or manufacture one tube, and then it's easy to manufacture any tube or, analyze any tube. And same applies for plates. Next. So then throughout the webinar today, we'll also compare kind of the industry approach with the high-powered rocketry approach. So the structural design process, I have a link to an engineering Wikipedia page, engineering design process. So feel free to go look at that if you're not super familiar with an engineering. I don't think I put the live link in there, Chris, but so basically you develop a complete, I think we talk about on the next slide. So basically you're trying to develop a complete product. You're using simulations, calculations, research, trade studies, testing, numerous, approaches and tools. And then you're trying to understand the performance of such product, via simulations, calculations, research, prior to building that product. Just like any, science experiment, it's the same thing that you learn in school. And then the product must satisfy criteria or requirements. These are usually set forth by the customer. Usually in industry, it's called an RFP, a request for proposals. And then here, your WSG CF&L is your customer. So we are the ones who set forth the criteria and the requirements that you need to satisfy with your product. And then tests and simulations are used to verify the product. So once it's done or nearing completion, to make sure that it satisfies all of the requirements. Next. So a little bit more about the engineering design process. So we start at the top of the slide. I guess you guys can't see my mouse, but defining the problem at the top. So we kind of give you the problem. We're saying that, you need to develop a rocket that does such and such. Brainstorming solutions, that's kind of up to you guys. All the different ways you want to fabricate. And then the next one, researching ideas and exploring possibilities. And that's same thing up to you guys to decide that. Establishing criteria and constraints. This is us. So this is kind of the handbook establishes all of your criteria and constraints. You're limited which solutions are possible based on what's given to you in the handbook. Considering alternative solutions. Again, if this was kind of just any engineering project, you could consider all alternatives. Selecting an approach. So you should be meeting now with your teams, right? And kind of narrowing down, well, how are we going to approach this project or this problem? And then the one at the bottom, developing a design proposal. That's the one that's due in the next couple of weeks. So that's where we're at. And then the next one, making a model or prototype. So again, if it's a big, it's a lot easier if it's a smaller project, like if you're just engineering a cup or you're engineering a pen, right? It's easy to make a small model and prototype. If you're engineering a big vehicle, you can't really make a big model or a big prototype of a big rocket all on the first go from a concept. So with your guys' projects, you'll kind of make smaller, models and smaller representative, components to help you solidify your design decisions. So then you'll test and evaluate those choices in the next step. And this is kind of thinking, January, February timeframe, preliminary design, refining the design. So based on the results of those tests, right, you'll refine the design at preliminary design and critical design in January, February, March timeframe. Creating your solution, right? So this is kind of, we've studied all the alternatives and possibilities, and now we are 100% confident that we know how we're going to build and fabricate this rocket and ensure that everything works 100%. And then communicating the results. That's just kind of attending launch weekend and flying the rocket and showing us, and it also applies to the reports as well. So being able to convey your solution, your ideas in your reports and in your virtual presentations, communicating those results to us, and as well as launch weekend, showing us that the rocket works as designed and satisfies the problem. Next. So structural design requirements. So if you don't already know, requirements are found in the competition handbook. There's a lot of requirements, not just structural in there. There's recovery requirements, avionics requirements. There are team requirements in there. So we just put a little example in here. I believe this is from the Mars requirements of the competition handbook. So you can see down at bullet number 2, materials, teams are limited to using carbon fiber and fiberglass cloths. So those are kind of some of the requirements for structural. So make sure you understand the handbook, what's being asked of you, what limitations are put on you, what materials you can and cannot use. And if there's any questions, like any confusion about what you want to do, feel free to reach out, email myself or Frank, or you can also just write them up in your reports and we'll give you feedback post reports. Next.
Oh, sorry. There you go.
Industry structural design. So how do we do the design in industry? So typical design tools include usually like a 3D CAD modeler, and there's various ones. There's CATIA, 3DX. I believe as a student, I used SolidWorks, which was kind of a lighter version of CATIA. And now we use Creo at Blue Origin. And then there's also usually a PLM, which is a product lifecycle management tool. And that's kind of how you store all of your data, all of the models and all of the analysis associated with those models and all of those components and assemblies, and allows you to bring everything together as the assembly, right? Because you may only be working on one part, but you also need to see everyone else's parts. That's what the PLM and the CAD modelers do. So usually your design is based on a previous design or similar product. The rockets we build now at Blue Origin are based on similar rockets, that NASA built or someone else built in the past. And the tools allow for design integration. And then, future revisions or future products that we're going to build will use the models from previous products that we have built. Industry standards usually simplify the design practices. So a beam is a beam, a plate is a plate, a shell is a shell. We understand these mathematically, and they're taught to you in your coursework, right, in mechanics and your dynamics class and your materials class. And then parts are utilized where necessary or where we see them fit. So kind of just instead of deciding to engineer and manufacture a beam or a motor or a pump, we'll decide that, hey, we're just going to go buy someone else's pump or someone else's beam off the shelf, and then use those in our product. Saves us some time and effort instead of having to reinvent everything from scratch. Next. So high-powered rocketry structural design. So your design tools will include RockSim. This is the required simulation tool. So hopefully all of you are aware that you are to use RockSim, and you've all downloaded RockSim and installed RockSim and began using it. We have some resources available. I think we have some videos on the WSGC website. We will have a webinar in a few weeks on RockSim. And then in the competition handbook, in one of the appendices, there's a lot of information on RockSim, how to begin with it. You can start with the trial version before you move up to the paid version. And so every member of the team should be learning RockSim and acquiring RockSim. Other design tools, 3D CAD modeler, not required, but it's optional, I'd say, especially for this year, since a lot of you will be 3D printing and your prints require CAD models, that you're going to have a CAD modeler and you're going to be CADing up certain components in CAD. And then 3D models also make integration easier. So allowing all of your parts and assemblies to come together and making sure everything fits together is great for CAD modeling. Your design will start from a blank sheet, so you will have no previous experience or data to pull from. And this is kind of just based on the challenge. I mean, some of you, the teams are returning teams, so you know rocketry already, you know kind of what to expect for as far as the simulations or the components go for rocketry. But every year the challenges, so you will have no previous challenge knowledge to pull from. That's kind of what I'm referencing there. And then rocketry rules will constrain your design. So these are listed as the requirements in the competition handbook. For example, the 3 kits for this year constrain your design. So your rocket as built on launch weekend will look like or duplicate one of 3 kits that are found in the handbook. Next. Structural materials. So choosing the right material involves understanding all the material options. So we kind of try to narrow down the options, right? In industry, there's a lot of options. We can choose from basically anything on the planet, as much as we wish we could, but usually the finance guys kind of don't like us choosing the really expensive stuff or high-performing stuff. But and then keep in mind there's different materials for interior versus exterior components. Some components are major load carrying, otherwise known as primary structure. And a lot of the other components, minor load carrying components, are called secondary structure. So they'll have kind of different requirements and usually made of different materials. Keep in mind environmental effects when selecting your materials. So thermal expansion, for example. So if you're building 3D print, PLA or ABS, the coefficient of expansions are different. So they're going to expand differently based on where you're flying. If you're flying in a cold environment or testing in a hot environment, and then you come to Wisconsin and it's a different environment, you're going to have different effects. Even just mating your materials together, right? You're going to have a composite piece next to a 3D printed piece, and in the cold they'll contract differently, and so they may not fit together anymore. So keep the thermal environments in mind when selecting your materials. The customer may also limit your material selection. So again, your customer is us. We've limited your material selection, so make sure you understand the requirements in the competition handbook. Next. So in industry, right, like I said, it's a balance of cost, performance, and weight. Engineers are always after performance and weight, and it's the finance guys kind of reel us back into reality and tell us it's the cost. It's cost way too much to build something that's super light in industry and super high performing. So you're trying to balance those 3. Cost may be an issue or concern for you on your teams, and that's kind of where we want you to run a budget early on in proposals, kind of weigh out, well, how much is everything going to cost? Maybe you do want the super fancy high-end composite materials, but maybe your budget doesn't allow that. So, you're going to kind of have to balance all 3 of those as well for your projects. New materials are developed alongside the design. So in industry, usually when we're developing a new product, we also develop new materials to go along with that product and a small kind of incremental changes for those products. Operating environment is a huge factor in industry, right? So our rockets deal with the vacuum of space, which is cold, and then they have to also deal with thermal reentry, which is hot. So there's a wide range of environments that we're dealing with. And fortunately for you, your environment pretty much stays the same over your flight. So, but where you are now in building your rocket is a different environment than where your rocket will fly on launch weekend. So keep that in mind. Fatigue and damage tolerance are also factors when choosing structural materials. So some materials are brittle. They don't like being cycled over and over, and some are better for cyclic and damage tolerance. Next. High power structural materials. So commercial off the shelf HPR, high power rocketry materials can be classified as. So you can see there, right? There's usually phenolic tubes, fiberglass, carbon fiber. There's kind of a set of standard materials that we use for the COTS high powered rockets. And then the point this year, the challenge this year is you're not going to use a COTS high powered rocket. So you're allowed to kind of step outside of those HPR materials a little bit and see what kind of show us what you can do. Typically teams will use mainly COTS components because of safety concerns. COTS components reduce the chance of structural failures. May be difficult to ascertain your fabrication and test facilities or testabilities. However, this year the challenge is to fabricate your components. So please include as much detail as possible in your reports. Next. So HPR structural materials. So we'll get in a little bit detail, right? So we asked you to 3D print a lot of components, especially for Moon. So some of the components that are possible, right? We have some nose cones, bulkhead centering rings, fins, and avionics sleds. So there's an example of some materials there. So there's
And
a
Mark, I do
3D.
believe you meant to say Mars, correct? Especially for Mars versus Moon.
No, mostly for Moon. I mean, both
Okay.
Moon and Mars will be 3D printing. Moon will mostly be 3D printing and no composite. Mars will be mostly composite with a little bit of 3D printing. So we started with the 3D printing because that's the easier option or the easier fabrication option. So you can also see where the CAD comes into account, right? A lot of the CAD models for your 3D printed parts. So you can make nose cones, fins, center rings. You can also make tooling. There's a fin alignment tool there in the bottom lower right. There's also a, I don't have it listed, it's a motor retainer, the little gray part in almost the center of the screen. So you could also 3D print those instead of purchasing that. So materials, you know, your standard 3D printing materials, ABS plastics or PLA plastics. Kind of depends a lot on which 3D printers you guys have. Kind of ties to the fabrication processes. The fused deposition modeling is kind of the one I'm familiar with, and it's probably the one that most schools will have is the FDM 3D printers, which use the ABS and the PLA. There is a stereolithography printer, and maybe some of you schools are fortunate to have more advanced printers, liquid printers or laser printers. So please just put those in your proposal and let us know what you're going to build with them, and that you guys are ready and know how to operate your 3D printers. And then also one thing to keep in mind for when you're 3D printing parts, right? So it's not just as simple as, hey, I'm going to print this part and it's going to go on the rocket, right? Because you're trying to make the lightest possible structure, thickness of your part is very important. I'm not going to say you want to make it as thin as possible because then it's a chance it's going to fail. So you do have to do some testing and experiment and calculation with your 3D printed parts. You know, like the resolution, if you're printing it fast or slow, how much material it's putting down, and the rate is putting it down. And then using the infills as well. On the nose cone, for example, are we going to add, you know, like a hexagonal infill to add some strength while making the wall thin? And then it's a trade, how much infill for strength versus weight do we lose? So it's understanding those trade studies, and that's what the written reports are for. Next. So another one of your major structural materials this year are composites. My brain always takes composites instantly to mean carbon fiber. I'm very used to working with carbon fiber in industry. but it's not necessarily carbon fiber. You can see there's a picture there in the lower right again of a fiberglass tube, fiberglass airframe. Fiberglass is also a composite. So basically anything that takes multiple layers and kind of lays it on top of each other and then uses a resin process in between the layers is known as a composite. So the components you can make with composites, right? Nose cone airframes, couplers, fins, and then there's a lot of pictures there showing the different tubes. I think there's 4 pictures just showing tubes, and then there's 1 picture showing a nose cone. So please get creative. Please let us know what you want to build and how you want to build it and what the material selections are in the proposal. And yeah, we'll give you feedback. If you got any questions, let us know. So your materials, right? Fiberglass cloth, carbon fiber cloth. And again, with those cloths, there's a lot of variation. There's various weights of cloth. You know, do you want to use a thinner cloth and just have 2 or 3 layers, or do you want to use a thicker cloth, you know, for strength? And then there's a lot of different weaves as well. There's, you know, like a plain weave. There's different weaves that allow for drapability. And those different weaves also have different weights and different strengths. So make sure to research and understand which material you're using. One of my suggestions during the testing or concept phase, use the fiberglass cloth. It's a lot cheaper, you know, to kind of mock up concepts before you get into the carbon fiber cloth, especially a component that it's just going to break or you're testing into destruction anyways. And then you could switch to the carbon fiber cloth. So again, fabrication processes, there's various layups and various cure methods. We're not limiting you to anything other than what your school or equipment is capable of. So you can do vacuum bagging, you can do resin infusion, you could use an autoclave for curing, you can do room temperature cure. There's various different ways you can cure your composite materials. Next. The structural analysis process. So yeah, we're good. Must ensure the vehicle satisfies the performance parameters and must ensure the vehicle can withstand the expected loads. So this is kind of what I do at work. You know, it's just checking the load and sizing the components to make sure that the component doesn't break over the life of the vehicle. So we perform analysis to achieve this, right? Simulations or calculations. And if the results of your simulation and calculation do not satisfy the above, you basically change the design or you change the material, and then you repeat the analysis. So typical analysis tools include finite element modeling, FEA. There's various FEA tools there, Abacus, Nastran, Hypermesh. You tend to use quite a number of them, depending on which program and company you're with. There's quite a number of flavors of finite element tools out there. Computational fluid dynamics, ANSYS, right, gives you some fluid flow calculations you could do. And then we also do hand analysis, and we use proprietary tools. So we could, yeah. So structural analysis for launch vehicles is very detailed. Loads are developed early from finite element models, aerofems, and then internal loads models distribute the load to the components. So it's kind of like taking the big picture first. You kind of get your overall vehicle loads, and then you start zooming in on the smaller components, and you look, well, what external load is my little small component or local component seeing? So that's what we do in industry. And then classical analysis methods, right? Like I said earlier, plate, shells, beams, everything kind of breaks down to just basic, 6 or 7 different components. And then we're looking at bending, torsion, buckling. We're looking at joints. We're doing free body diagrams and load pass. And then we size the parts to minimize the weight. So, you just want the part just big enough to be able to withstand the maximum expected load. The problem is if your predicted or your expected maximum load is a little higher than you thought it would be, then your part's going to fail. So you need to have a little bit of extra kind of buffered in there and make sure you understand your max load to size your part to be as small as possible, if that makes sense. Next. So high power structural analysis. Your analysis tools will include RockSim for vehicle performance and for loads. If you kind of run simulations, RockSim can give you forces and accelerations anywhere along the flight envelope based on what vehicle and what mass you have in there. So it doesn't really do a detailed, you can't see the loads on each component, but you can kind of see it overall expected loads on your vehicle, on the thrust phase and on the descent phase. So you could use those loads to help you do some material selection and analysis. You may use additional simulation methods. So you could use another simulation tool such as OpenRocket to verify or back up your RockSim. But RockSim is the tool you use to submit information to us in the reports. You can also use other simulation tools, like if you want to run a CFD or you want to run something, in a wind tunnel, or you want to make some MATLAB code, to help determine loads or internal loads. By all means, feel free. And you also use hand calculations or FEM or test for component analysis. So we're going to want you to, as you build your components, we're going to want you to test them or create a FEM for them to load them up, or to just show a simple hand calc to show that the component's thick enough or strong enough to withstand the expected load. And that leads us to the next one, understanding your maximum load and forces. So which components experience the highest loading? What direction is the max load? When does the max loading occur in flight? And then your material selections are based on your loading criteria. And like I said, you may use CFD to characterize your performance. And tests should definitely be used if there's any uncertainty in the strength of your components. And we'll get the test later on. Next. All right, structural tests and components. So during the design and analysis phase, such as the proposal, PDR, CDR, you'll begin your structural tests for your fabricated parts, such as your 3D printed or your composite parts. You'll test to show that the component max load, show the component max load or failure. So you just want to size your parts again to withstand the maximum load. You could test your part to failure. You could say, hey, I got a flat plate here, it's a fin. I want to know how much force I need to push down on this fin to be able to bend it until it cracks in half. Destructive tests I always thought are cool, right? I mean, just as long as you're using the proper PPE and safety procedures, you don't want any of the destruction kind of injuring any of your team, but that's kind of, you're usually not designing to destruction. You just kind of figure out your max load first, and then just apply the max load on that component and ensure it can withstand that maximum load. If you want to test the failure, that's to your own detriment. Also, testing to failure costs money, so they don't like us testing to failure in industry. Tests are required, so know the strength and properties of your material. Test your bonding materials and bond strength. So that's another one that we usually tend to forget, both in industry and in HPR, I would say. So you could have the two strongest materials in the world. You could have two perfectly, manufactured and examined and finite element model parts. You stick them together using some epoxy or some screw or some method, and basically that's the weakest point now, that join, and then the join separates in flight. So make sure you understand your joining, your bonding, and your bond strengths. So there's a list of structural tests that can be included. Again, none are required. It's up to you to come up with your own tests. And then tests should be conducted early in a program. So have a plan in your proposal. It's kind of a requirement for both the Moon and Mars teams to have a test plan in mind for testing all of your materials and configurations. Next. So in industry, we use what's known as a test pyramid. If you look at the bottom, it starts at the bottom. You do a lot of coupon tests. So it's kind of just a small, you're just testing the material basically, and you work up to elements. Coupons are kind of just flat rectangular sections. You move up to element, and element could be like an L channel or a T or U. And then you move up and you start testing details. So you'll test a hole, or you test a C beam, or you'll test an I beam. And then you move up to a component testing, which is kind of like an assembly or sub-assembly. Say on an airplane, for example, you want to test the entire wing. So you're going to do a test on the wing itself, before it's attached to the vehicle. And then finally, at the very top of the pyramid is a full kind of structural test, especially for human-rated vehicles. The FAA, requires, mandates us to have a full static and fatigue test for your full vehicles. And like I said, new materials are developed alongside. Testing is conducted alongside design, so they're kind of working in parallel, right, to shorten the lifespan or shorten the design time. The design's kind of working with the test. Sometimes design might be banking on the results of a test. You're kind of expecting a test to come out and not fail. And so you design all these parts and you're like, okay, well, the material is going to be good. And then the material fails. And now you're stuck with this design that doesn't work anymore because it's going to fail in flight. So then you quickly have to scramble in industry, or, you have to change things around, change your design or improve your testing methods or improve your material. Next. So high-powered rocketry testing. COTS structures do not require testing usually. They're usually over-designed. You're interested in ascertaining the limits of your material, developing and understanding the testing of fabricated parts. So it's not just about the material or testing the material. It's kind of like developing the process to test. And like I said, if you develop that process on a small coupon, and then you can immediately kind of scale that up and develop it on, and use the same process on larger components and assemblies and full-scale vehicle. So you could sample test the failure, like I mentioned. So for all your fabricated components, you should do structural testing. So there's your components, and there's some suggested tests you can do. You may want to use a similar test pyramid as industry, right? So you don't want to wait till the very end of your program till you have the full vehicle to test it, and you haven't tested any coupons, you haven't tested any materials, you haven't tested any assemblies. And then, it fails, but you don't know where it failed. It could have failed at any of, dozens of points. It's kind of good to test along the way, testing coupons, components, and assemblies as you go, and kind of reduce the chance of those components failing and risking the entire vehicle. Next. Manufacturing integration. Structures should be designed for ease of manufacture, assembly, and integration. So keep manufacturing in mind when you make a part or material selection. Will this part be difficult to manufacture? Will this part be difficult to integrate? Is the material easier to work with or difficult to modify? So many good designs become terrible products when changes must be made because assembly and integration aren't taken into consideration. So that's kind of, you design all these wonderful parts and you go, in March and you want to put them all together and you realize things don't fit or something, and then you have to go back and change your parts, or you have to kind of, funkify the integration and the manufacturing, the assembly steps. And now you've kind of just sacrificed and wasted all those perfectly designed parts. Now your overall vehicle's going to suffer. Next. So industry integration, right? Fabrication begins as design winds down. So again, you're overlapping the design processes. So the first few units are very slow to fabricate. You can see there's a picture there of the SLS being kind of assembled and integrated, the sections stacked on top of each other. So it's usually more than one unit. Fabrication, right? Some things like rockets, you're only developing very few units. Something like airplanes, you're developing hundreds of thousands of units. For you guys, you should be developing one, maybe 2 units, maybe one full-scale rocket, at least one full-scale rocket, and maybe 2. You might want a backup rocket. So in industry, right, there's various supply parts fit together or must fit together. It's all not just one person. You guys are fortunate. It's all one part. You shouldn't be subcontracting your parts out to someone else and then bringing them back. Tooling usually begins during design as well. Usually the tooling is a long lead item, and usually tooling is very hard to change. So keep that in mind. You guys are fortunate. You don't have much tooling to do in your smaller high-powered rockets. The certain parts don't fit, needs to be changed. Yeah, I guess you could. Not advisable. Again, that's kind of why we do the design reviews. So if we feel like something's questionable early in the design review, we'll kind of examine it in a little more detail with you. So, you'll be submitting your rock sims, you'll be submitting written reports, you'll be submitting, performance statistics. And then we have a lot of reviews every couple weeks. So you should never get to the point where you're, 4 months in or 3 months in, for example, and then suddenly you find a problem. We should always kind of discover them within a couple of weeks of it happening and help you make those course corrections. Yeah, so design analysis may change, right? So we kind of mentioned that a little earlier. Sometimes you erroneously do get to a later stage in the project and something's wrong and you have to go back and fix things. So in the industry side, there's manufacturing guys work with the LISAM, work with, guys like myself on structural design, structural analysis. You all kind of got to work together. The upstream and downstream guys all work together to make sure everything kind of fits as you go. Next. So HPR integration. So right, COTS components should easily integrate. You buy your COTS kit, you buy your COTS rocket, the coupler should fit inside the airframe, 99.9% of the time. I mean, I guess there's the odd occasion where there's a burr or something defective and it doesn't fit, or they sent you the wrong one in the kit and it's too big or it's too small. But integration with COTS is pretty straightforward. However, for this year, right, you are fabricating much of your components and you are mixing parts. So integration will be a concern. So you need to make sure all of your stuff fits together. So make sure you leave time in your planning and your proposal, and sure you leave time for fabrication and integration. So your challenge components, right? And that's all the components you're manufacturing. They should all have an integration plan. So you'll use CAD modeling to assist with your parts integrations. There's a nice picture in the upper right there of a rocket that's kind of CAD modeled up. And you can see all the components, how they all line up, and then everything's kind of manufactured to fit together properly to the right dimensions. And then when you fabricate, it should all line up with the CAD and fit together properly. Another one you could do with your CAD modeling as well is in the lower right is kind of an avionics bay. So smaller details and assembly should also be CAD'd up to make sure that, okay, hey, we can fit this battery beside this GPS, beside this, altimeter, and here's how everything's going to work, and here's where the switch is going to sit. It's a good thing to CAD that all up ahead of time, so you'll know that it all fits together. I think I've seen teams in the past who didn't really pay much attention to integration. They had this wonderful idea. They're like, oh, we're going to put this controller and camera and all this stuff into the avionics bay. And they go out and buy it all. And then when it shows up, they realize it doesn't fit. Nothing, half of it doesn't fit in the area that they thought it would. It's because they didn't pay, any attention to the integration. So pay attention to integration, use CAD models. Next. So structural testing of the vehicle, right? So most products undergo rigorous testing, not just Rocketry products, but any product basically that's put out for consumers. Human rated vehicles undergo a lot more testing than not human rated vehicles, or components. And then testing must also ensure that the product is safe. So that's the point of the tests. It runs through its life cycle to ensure that it doesn't explode or blow up or damage anyone or go off course. So next. So right, like we said, rockets, full-scale tests. There's an autonomous flight test, so no one's on board the very first flight. We put it all together. The computer's running everything. You hit the go button and the rocket goes. Not just for Blue Origin. I think all vehicles, the SLS, the very first flight of SLS will just be an autonomous flight. There's no one on board to test that vehicle to make sure it can achieve its objectives. And then for aircrafts, which I have some experience coming from the Boeing company, same thing with full-scale tests. You do a full-scale static test. To failure, the picture in the lower right there, you can see the wings of the airplane are deflected up at a significant deflection. So if you're flying on an airplane and you see the wings moving, it's normal. It's fine that the wings move. The wings can move to that position. If you ever see the wings in that position, you're still good. We still design it to be a survivable flight in that configuration. And then we do a full-scale fatigue test as well. So it's kind of just cycling your components over and over. You won't need to do those for your high-powered rocket. And then we also do fleet performance flight tests. Next. So if you're a high-powered rocket, your structural testing, and I should say vehicle, we recommend that a flight test be built into your schedule and performed prior to competition launch. So note that it's not required, but it is recommended. You may want to fabricate a spare airframe if you damage your airframe in flight test. And I think we've seen that before, where teams have done a flight test and something went wrong and they've damaged something, and they had to quickly scramble to build a new airframe or to build a new component or something in time for launch weekend. So keep that in mind. If you are planning a flight test, make sure to have either spares on hand, or if you test everything ahead of time, maybe the reliability of your test, you might be pretty confident that your flight test is going to go off fairly well. So your flight test will also validate your structure, and it validates your simulations. So you could adjust or dial in your simulations based on your flight test to help you have a better performing vehicle on launch weekend. So work with your rocketry mentor. Again, we had a webinar a few weeks ago about rocketry mentors, so check that out on the WSGC website. If you don't have a rocketry mentor yet, please get in touch. I know many of you do. I've reached out to a lot of the advisors and help you get a rocketry mentor. Your mentor will ensure that you're following safe rocketry procedures during a flight. Your mentor will assist you with getting a motor procurements for your test flight. And do not plan a launch without a certified mentor. Next. So we can go over some structural failures, some typical failures here. So usually we see eye bolts and bulkheads fail. So that's the picture in the upper right. Your eye bolts should be sized properly. So you should know the load or the amount of load that's pulling on those eye bolts. Every eye bolt will have, it might have stamped on the eye bolt itself, the rating. It'll say something like 3,000 pounds or 6,000 pounds that it's rated for. So don't just arbitrarily pick an eye bolt, could be 1,000 pounds, and then your flight, you actually pull 2,000 pounds. You're going to deform the eye bolt, and you're going to wreck your flight, wreck your rocket. Another thing to note about the eye bolts, get a forged eye bolt. So that's the eye bolt in the top that's kind of closed, versus the folded eye bolt, the one that's bent around. So again, those bent around eye bolts will tend to open up with the load, whereas the forged one will not. So make sure to get forged eye bolts versus the bent eye bolts. Another thing to consider is a zipper event. This is kind of primarily occurs on a phenolic airframe, but it will also occur on a fabricated composite or airframe. So a zipper event basically is when the shock cord comes out of the airframe's accelerating down, but the shock cord is accelerating up because the parachute is opening, and eventually you're left with the torn, as the middle picture there shows. The shock cord will zipper or tear through the airframe, and it leaves a big crack in the middle. So that's something to keep in mind. You might want to strengthen the area around the ends of your tubes to make sure that you don't have a zipper event, or just sizing your shock cords properly will also eliminate a zipper event. Next. Some more structural failures. A CATO, known as catastrophe at takeoff. That's kind of a picture in the upper right. It's like a motor failure. I'm not sure exactly what happened there, but you see just parts flying everywhere. Of course, we don't want that. And then the second picture as well, you see kind of pieces and smoke going everywhere. So that's usually when the motor mount is not properly restrained. It could also be due to a defective motor, like a motor failure. You can't control the motor failure because you don't manufacture the motors, but you can control the motor retention. So you can control the motor tube sitting inside the rocket. And again, I think we've had teams, or we've known of rockets in the past where the motor, the center rings or the motor retainer wasn't properly secured. So luckily we've caught that, and we haven't had any troubles with that. The middle one there, fin flutter divergence. The fins will flex or oscillate. So you can see in the third picture down from the top, the fins kind of bent at this really wicked angle, right? So fins will flex, oscillate. Again, fin flex and oscillate is fine. It's normal for the material. But because you guys are manufacturing your own fins, make sure your fins are sized properly. Make sure they're rigid. At a certain point of flex, the fin will diverge. Basically, it just breaks. It breaks off, right? Exceeds the bending. So that's why you kind of want to know the capability of your fin ahead of time before you go into flight. And then premature late separation, pressure differentials cause the airframes to separate in flight. So as your rocket goes up, as pressure in the atmosphere decreases, the pressure inside your rocket stays the same because it's closed up. So, using vent holes or using shear pins to remedy this to make sure that your structure does not separate in flight. Next. And take it away, Chris. You can have this one.
Excellent. Thank you so much. So just want to go over what our future webinar schedule looks like. The Zoom link is always the same every single week, and pretty much until the end of the year, right before Christmas, we'll be meeting every Tuesday afternoon at 4 p.m. Central Standard Time. So, pass it out to your teams. And we also, I believe Connie sent out a link to the fall flyers, so you can send that out to all of your members. What's coming up next week? We do have project management webinar, and that's November 22nd, Tuesday at 4 p.m. with Orson John, who is a reliability engineer from NASA Goddard Space Flight Center. So you don't want to miss that. He does a great job, and he's been a part of the program for several years. In when he discusses project management, he discusses it specifically to FNL, just not an overview from an industry perspective. Then the following week, on the 29th, we have Trent Cibella. Trent is a former Wisconsin Space Grant Consortium alum. He also is a mechanical design engineer at Sierra Space Corporation. He helps us both with First Nations launch and with our collegiate rocket launch here in the state. And so he does a fabulous job of taking you step by step through the RockSim application and helping you to understand it and utilize it to the fullest of its capability. And then we have rescheduled the proposal, budget, and design review development webinar. That is going to be Friday, December 2nd. That was the availability of our host. So again, 4 p.m. on Friday, December 2nd, and that is Genevieve Benali. And she is with Raytheon, and she does a great job presenting. Now, what is not on here, so please take note, December 6th from 1 to 3 p.m., we will have office hours. And our office hours are specifically designed for you, any person on your team collectively, to come and ask questions specifically about the competition, the engineering parameters, or the proposal. And we're going to be there to answer questions for you. And so as your schedules allow, you can pop in and out, and it will be the same Zoom link. Then lastly, we have the build and assemblies techniques webinar, and that'll be on December 13th. And again, Adrian Guthner, he is another alum of our program. I believe he's level 3 rocket certified and is a mentor for our statewide teams. And so he will be giving this year's webinar on build and assembly techniques. Lastly, award acceptance. The award acceptance materials were due yesterday. If your school has not submitted the acceptance material, there's a couple things that are going to be on hold. Number one, you cannot spend money unless we have the award acceptance material in hand. That is what gives you the go-ahead to that we have an agreement with you to be able to spend money. So please, 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 please make sure you get in your acceptance material. If you have any questions, Connie can assist you. And it isn't sending it in to us in an email, it is uploading it to your grant management page. Second, we have low powered rockets, the Estes rockets that we are going to be sending out to you to do that launch that is required. And we cannot send that out until you have submitted your award acceptance material. So with that being said, if you're a northern team, we know that you guys are dealing with snow probably already. I know Wisconsin got some. Here in Missouri, we got some too. So there's snow coming all over. And if you want to be able to get that rocket so that you can find a good, clear day to launch it, we need to have the award acceptance material in hand so that we can ship that out. So for those of you who have submitted your stuff on time, Connie will be sending out your rockets tomorrow or today, and then, or tomorrow, one of the two. Anyways, this week. If you have not, your rockets won't go out till next Tuesday when she's back in the office. So it's extremely important that you get that paperwork in so we can get you your rocket out. So we finish up with slide number 31 with 8 minutes and not 10 minutes, but 8 minutes to be able to answer any questions that you may have about materials, fabrication, or structural topics, or anything of the like. We're here to answer those questions. And thank you, Mark, for giving the presentation. Lots of good information. Questions?
Yeah, Helen Raposa from Honolulu Community College. I do have a question. On slide 8, you make a reference to the PLM software. Product lifecycle management. Are there any recommendations or examples of this software?
That's you, Mark.
Yeah, we use, there are things like Innovia. I don't know if you're looking to buy, it's probably, I mean, they're probably very expensive to buy this product lifecycle management. It was just kind of an example from industry, not recommended for teams, but Innovia is the one. They're the same company that make the CATIA 3D CAD modeling software as well.
Okay, all right. Thank you very much.
Other questions?
Hi,
the
it's
question
Cameron.
is asking who is responsible for the award acceptance letters. So it is sent to the advisor of the team. So the advisor is responsible for uploading them to their grant management page. Now, the way the system is designed, a representative, if the advisor has selected an authorized user, typically somebody from the grants office at their institution, that individual can upload that information on behalf of the advisor. If you are a co-advisor, again, you're linked to the award acceptance materials and uploading of documents, you as well can upload that information. And I believe, Connie, you can correct me if I am incorrect, but I do believe the team lead can also upload that information.
Yes, they can.
Okay, so there's four individuals: authorized user, advisor, co-advisor, team lead, and only one person needs to upload it for it to be recognized as submitted. Okay, there was another question, I believe.
Yes. Hi, it's Cameron from Queen's University here. I was just wondering for Mark if we made our own cardboard, if that would be acceptable using basically resin fusion techniques, but using basically paper as the cloth. I was wondering on your thoughts.
Yeah, I don't know. Frank?
Yeah, the cardboard will work good as long as you're using. Are you going to be using a resin with that, or are you going to be soaking it in pig oil, or what?
Not sure yet, but it was just kind of exploring the possibility of it.
Right.
I guess it does meet I'm just thinking, I'm like, I'm thinking of the weight thing. I'm like,
Right.
density, and I'm like, well, it's not as strong as carbon fiber, right? But you would probably need more of it in the axial direction to, not buckle, or, to even the hoop strength. But yeah, you could put it in your proposal and just make sure to have a plan B, and as you go through those tests, make sure to fabricate and test your materials, test your components.
Yeah, for sure. Thanks.
Any other questions?
Helen Raposa again from Honolulu Community College on slide 26.
I gotta be careful what I put in my slides from now on. Helen's
Okay.
gonna be all over.
The thing is that even though we have pretty good weather here almost year round, we do have an issue with finding big enough space to go to 2,500 feet. So if we do a test flight, is it okay if we do like a lower altitude, like maybe 1,000 or 800 feet for our gateway challenge?
Yeah, that's kind of why it's just recommended, because we know
Yeah.
certain teams cannot have test flights. So we can't make it required. Otherwise, we would make it required. So no, it's completely optional. It's up to you guys. If you don't have time and resources to flight test, then don't bother.
Okay, yeah, I just want to know about that part. Yeah, thank you very much.
Any other questions? If not, I do want to thank everybody for coming. Remind you that next Tuesday, we will have our next webinar. Please don't miss it. It's going to be great. And in the meantime, if you have any questions, feel free to reach out to Connie, Mark, Frank, or myself, and we'll be happy to assist you. And wish everybody a great rest of your week. And we'll see you all soon. Thank you.